Yeah. No, sir. Okay. So, okay, maybe we can get started. We are very happy to have Suvrat with us today. He's going to tell us about cosmological correlators and de Sitter and gravitationally constrained states. Okay, thank you very much. So this is actually about some work in progress, which is with Ashik and Tuneer. And it's a follow-up to a paper that we wrote now a couple of years ago with Tuneer and Priyadarshi and Victor and Joydeep. So this was actually meant to be an informal talk. So even though it's a string seminar, the idea is actually to keep it informal. And our paper is not yet out. So it hopefully will be out. It should have been out some time back, but it will hopefully be out in very soon. We'd really appreciate feedback. So if you have questions, please interrupt and ask, and please treat this as informally as possible. I'm happy to address as many questions. Okay. So the way I'm going to structure this talk, so this is about cosmological correlators, in gravitationally constrained de Sitter states. And the way I'm going to structure this talk is, first I want to talk about a review. This review has to do with this part of gravitationally constrained de Sitter states. So this is, I'm going to review give you a very quick review of what we did in this paper a couple of years ago. And then I want to talk about perturbative cosmological correlators. So I'll talk about first the second part of the title and then the first part. And then the last part is about relational observables. Okay. So relational observables are also going to be cosmological correlators, but they're slightly more complicated observables, not things you can define very straightforwardly in perturbation theory. So that's how I'm going to do it. Yeah. Okay. Good. So are there any questions about the overview or where I'm going or anything very general before I start? Okay, good. So let me start by describing to you what these gravitationally constrained states are. So previously, and there have been many talks on this, and also been many talks in this. So this audience is probably familiar with this. We looked at metrics that had the form that they were asymptotically de Sitter space. I don't like this colored chalk. I'm going to use the orange chalk because the colored chalk somehow has more dust. I hope you can see at the back. Yeah. And what we did is we found all solutions. So we found all solutions of the gravitational constraints for metrics which had this form asymptotically. Okay, so that means we identified all solutions which were functions of the metric, all wave functions which were functions of the metric, and of some matter fields. I'll denote the matter fields by chi, which satisfied the constraints of gravity. Okay? Now, in fact, in this talk, there's some structure to the solutions, but I'll try and come straight to the point. So I'm not going to use the full structure of solutions that we found. This talk is about the non-gravitational limit. So this story is slightly simpler, the non-gravitational limit that I'm going to talk about. Sorry guys, 1 second. I should check this earlier. Sorry. As you all know, I like to have this AC down, and I hope this one is also on. Yeah. So this talk is about the non-gravitational limit of these solutions. So this talk is going to be about a simpler story, and this story of the non-gravitational limit of these solutions has actually been understood for a long time, from the time of Higuchi, in fact, and then in many other ways. But I'm only going to focus on the non-gravitational limit of these solutions. When I say non-gravitational limit, as I'll explain in a minute, I'm going to take
a non-gravitational limit starting with a set of gravitationally constrained states, which is not the same as not having gravity in the first place, as I'll explain. And so it's going to be about, but the metric in particular, it doesn't have to be, it's not asymptotically this, but it's just going to be de Sitter space. Okay? So I'm going to talk about the states in de Sitter space, which are constrained, but then I'm going to talk about how to take the non-gravitational limit. So what does it mean to take the non-gravitational limit, starting from the gravitational theory? It's, yeah.
When you say you're taking this metric to be de Sitter,
yes.
That means you're looking at those
Yeah. Yes.
You normally would have a wave function.
Yes, I would have a wave function, you're right. And so I'm being a little sloppy when I do this. You're right that I should really consider the metric as a function also of I should consider the wave function as a function of this plus transverse traceless fluctuations of the gravitons, which will also survive in a non-gravitational limit. They'll just be free gravitons and also matter fields. In this talk, I'm actually just going to consider a scalar field that's propagating on top of this. So I'll forget about the transverse traceless gravitons, but it's pretty easy to add that as well. You're right that what I should really do is I should consider the wave function as a function of transverse. There'll be Gaussians, and I'll just not consider them just because we don't want to keep tensor indices, but there's no problem in considering them. Yeah? So you're right, I don't have to write exactly is equal to, I could write this plus transverse traceless, but yeah. Okay. I'm saying what I'm going to do in a minute. Are you still asking the same question about what transverse traceless gravitons? Doesn't matter. Let me remove that. The scalar field, yeah. So the scalar field I'm going to talk about in a minute. Yeah. Okay, good. So what is
like taking the G angles to 0?
Yeah, it's exactly taking G angles to 0. Exactly. So exactly as Rajesh said, you could ask the same question in Yang-Mills theory. Many people, when I was starting my PhD, Shiraz and others were asking this question for Yang-Mills on a sphere. So you could ask the following question. Think of Yang-Mills, and what is special here is that this is de Sitter space, but this is de Sitter space where the universe is closed. Okay, the spatial slices are closed. So you could do the same thing with Yang-Mills theory. You could take Yang-Mills theory, put it on a sphere, and then ask what happens as G angles goes to 0. In the limit where G angles goes to 0, you still, you can't just say, everything goes. You still have to impose the Gauss law on states. You still have to impose that states are gauge invariant. Okay? So what this means is still impose the Gauss law. Okay? And exactly as in the case of Yang-Mills theory, it's still an interesting constraint. So when you take the non-gravitational limit, it's not the same as not having any constraints whatsoever, but it's a rather simple constraint that you have to impose, which is simpler than trying to impose the full Wheeler-DeWitt equation. Okay, so that's all in this talk we are going to talk about. Okay, so in particular, there is one state that we can start with.
So when you mean Gauss law in gravity, you mean all the momentum?
No, so I'll say in a minute what. Or let me say it now. Okay, so what does it mean to impose the Gauss law in gravity? I was about to say it in a little more detail, but let me say it now. So you see, in gravity as well, there are charges that you can write down. The charges in this case correspond to the isometries of de Sitter space, okay, which are just the conformal group. So that's just SOD plus 1, 1. Okay. And you have to impose these isometries are implemented on the Hilbert space by some unitary transformations. And the Gauss law is the statement that the states that you have are invariant under these unitary transformations. So the Gauss law is a statement that the states that you have are invariant under the de Sitter isometries. Okay? Because, just the same way as you would have in Yang-Mills theory, these are what would have been the global charges in asymptotic de Sitter if the spatial slices hadn't been closed. But because the spatial slices are closed, you have to impose de Sitter invariance. Okay? So the charges under all the de Sitter isometries have to be 0. That's what imposing the Gauss law. The global Gauss law. It's a global. It's only SOD plus 1, 1. It's global. It's only the global part. Yeah. That's all you have to impose. You also solve the momentum. The momentum constraint is just telling you about gauge invariance, about that you have to write things in terms of locally gauge invariant things. So, the momentum constraint is actually a little trivial. It doesn't say much. It's just saying that you have to write things in a gauge invariant way. The constraint, another way you could have taken the full set of solutions that we had, which solve both the momentum and the Hamiltonian constraint. And you could have reduced them in the non-gravitational limit. And in fact, that's the same as taking the set of states you get from quantum field theory and restricting to the set. Okay. So I'm just reviewing right now what we did previously. Yes.
Maybe you,
yeah.
The non-gravitational limit, you take G Newton
to 0.
G Newton times.
No, you just take G Newton to 0, but you keep imposing the Gauss law. Okay.
Newton
times LDS to 0 if you like. I mean, you take G Newton if you want. You want to take G Newton. You can take G Newton times the ds scale as a cosmological constant if you want to take it to 0 dimension. I mean, dimension. You really just want to switch off the gravitational coupling. So it's not like there's a we are always at omega. We'll always be at omega goes to infinity. In the previous paper, we are talking about the late time slice.
Newton times omega squared. That was dimension.
Yeah, but here this is a simpler thing, right? When we really just want to switch off the gravitational coupling. So it's not saying so you just take G Newton goes to 0. Okay, good. So let me say a little bit about this constraint. So this is what we want to impose. Okay, so the main challenge, and this is something we did in a lot of detail in our previous paper, was that you want to take the set of states in quantum field theory and you want to impose this constraint. Okay, so there's one state that we all know and love that actually satisfies this constraint. It's called the Hartle-Hawking state, or it's sometimes called the Euclidean vacuum. And these are really the same, all names for the same state, or no boundary state. And it's also called the Bunch-Davies vacuum. And there are slightly different ways of defining the state, but it's really the same thing. And the way you get this state is as follows. You take de Sitter, you continue it to Euclidean space, you get this hemisphere, and then you do the path integral on this hemisphere, and you get some, you do the path integral on this Euclidean thing, you get some wave function. This wave function, since I'm not talking about the metric, it's some function, and this you can call this you can think of as a state in the theory, and this state goes by these various names. It's called the no boundary state because you do the path integral with only one boundary, okay? Only a boundary in the future, no boundary in the past, okay? It was proposed by Hartle-Hawking, that's why it's called the Hartle-Hawking state. It's the Euclidean vacuum because, if you take the states on this theory and you continue, you take the states in the Lorentzian setting, you continue them to the Euclidean thing, these are the states that are regular here. Okay, it's also what you would get by starting with de Sitter and trying to impose some boundary conditions on the past Poincare horizon. So that's how Bunch and Davies would have defined it. Yeah. So this gives you a state which I'll just call 0, and this I'll just call, so this is 0. So this is going to be my Hartle-Hawking state, and this state is famously known to obey this constraint, which is that it's invariant under the de Sitter isometries. Okay. So now you could ask, what are the other states in the theory? And to look at other states in the theory, you could try and construct a Fock space. To construct a Fock space, first, the simplest way to construct a Fock space is to take the fields in the theory and to act with the fields on this vacuum. Okay. Now, yes.
This other set of
alpha vacua.
Yeah.
Alpha vacua. The alpha vacua also do satisfy the constraints. You can think of the states I'm talking about. Yeah, they are also U invariant. The alpha vacua also de Sitter invariant. You can, one way to think of the states that we have. So the alpha vacua are not in the Fock space that you construct about the Euclidean vacuum. They're outside the Fock space. The states that I'm about to talk about, you can think of as kind of some derivatives of some of the alpha vacua at some of the alpha parameters. Okay, I won't say it that way, but you could. And then you set alpha equal to 0 after that. Yeah.
Right. But why aren't you considering the alpha vacuum themselves?
I just want to consider, the superselection sector that's obtained by taking the Euclidean vacuum and what you get on top of it. Those would be some other states in some other superselection sector which have some infinite particle excitations on top of it. So usually we would think that's a different sector of the Hilbert space. That's not.
I thought you want to consider all possible.
So indeed, when we write down the solutions, what we'll actually get will be some solution for wave functions. The wave functions, one of the wave functions will be this no boundary wave function. The other wave functions will be, these, you can think of them as these alpha vacua. Then, we try to define some norm on the space of states and try and define some set of normalizable states. Those are, so the way we define the set of normalizable states, so if you just solve the Wheeler-DeWitt equation, you will get all the solutions that you mentioned, is by looking at small excitations about the Euclidean vacuum and then trying to define a norm on that space of states. Now, it's possible you could define some infinite, some infinite Hilbert space, which was a direct sum of states built on top of all of these alpha vacua. But I would think that, those would be in different superselection segments. Like, I don't think there's any nice way to define a norm between, I don't think that, no, there's no tunneling, and I don't even know that there's a nice way to define a norm that would be finite between excitations in one sector and another sector.
So how do you know this? Because that's why sometimes the space is compact.
Yeah, how do I know that there is, the statement I'm making is, well, the statement is that I don't know how to define a norm that's finite between sectors between states built on top of one and one of these other states which have alpha not equal to 0, not if you take a derivative, but you just try and define the norm between one of these states and one of those other states. So basically the solutions you get from here are of the following kind. They look like e to the minus g2 times chi. Let me forget about g plus g3 times chi. I'm just writing down solutions where these things are constrained by the, so when I'm writing g2 chi, I mean okay. So I hope the notation is clear. So you get a wave function of this kind. The de Sitter isometries just tell you that these G2s have to be, constrained by conformal invariants. They impose some Ward identities on these G2s. The no boundary proposal. Yes, sorry. Chi-fx1, Chi-fx2. Sorry, thank you. Yeah. And similarly for G3 and G4. The de Sitter, the Wheeler-DeWitt equation just tells you that you have to impose some Ward identities on these G2s that basically tell you these G2s correspond to conformal correlation functions in a conformal field theory that's not necessarily unitary but satisfies the Ward identities. Okay. The no boundary proposal gives you a particular value of G2, G3 and G4. It gives you some specific values. Those specific values that you get are what you would get by doing the no boundary path integral. Okay. Then given those values, you can ask, let me take one of these guys and perturb it by a small amount. So let me take G3 and write it as G3 that you would get from the Hartle-Hawking plus alpha times a different G3 and put that, and then take the derivative of that state with respect to this alpha and then set alpha equal to 0. That you can think of as a small excitation with finite particle number on top of the original vacuum. You could also say, well, let me not take the derivative, let me just think of the whole wave function, okay, which has this value of alpha. You could probably do that. I don't know how to get there would be some additional subtleties in how to define the norm if you kept a finite value of alpha on with this. In fact, I don't know how to immediately,
So you're saying in general there will be a one parameter family?
Not one parameter, infinite parameter, because you can deform this in many different directions. You see, this is just constrained by conformal invariance. So the number of directions is like theory space. So the one way to think of it is that this is the Hartle-Hawking state. And then you have these different directions in which you can deform the Hartle-Hawking state. And what we are doing is we are kind of deforming by an infinitesimal amount and taking one of those states. You can ask now, what about the state that you get by deforming by an infinite amount? Or by deforming by a finite amount rather than infinitesimal amount. So
are themselves not something that you would.
So I'll never keep alpha non-zero. I'll always take the state. I'll take the derivative with respect to alpha and then I'll set alpha to 0.
But you could have, when you say if you were to keep it in the exponent, that would have corresponded to an alpha vacuum? Or?
That would have corresponded to what you might be able to call an alpha vacuum. Yes. So you could call one of these states. They all satisfy the de Sitter constraints. I think you could take G2 to be just the same, right? There's some discussion of what happens if you look at, I think we've also had this discussion, but so maybe first of all, which are not physical. So first of all, okay, so I'm not sure what you would call these states. These states are also, you can think of as alpha vacua. I think first of all, I might be using alpha vacua in a slightly non-standard way. But these states are also different vacua of the theory which are completely de Sitter invariant, which you could have. Now I should say that so when you you've explained this to me once before. Can you please explain to me how do you get a G2 which is consistent with conformal invariance?
You look at the invariant vacuum and find solutions because the point function is singularity not only at coincident points but also
when the points are on the opposite sides of the pole.
Yeah.
Okay. So you could of course do that. You could just think of just modifying even G2. I was thinking of modifying only the higher G3s and keeping G2 fixed. Or maybe G3 also fixed, but actually modifying G4s because G3 is also fixed by conformal invariance. No, but you could,
For your finite volume size, can you really distinguish this alpha vector from
Can you really distinguish? Well, what Alok is saying is that they have different singularities. The singularity structure is different. But what I'm calling these alpha vacua are just vacua where you have deformed some of these by alpha parameters and then you're taking the derivative. First of all, just by taking the derivative, it's a linear space, and I'll get a lot of directions in the Hilbert space. Now you could ask, am I getting everything? Am I getting the whole space of wave functions? And I'm not sure. And also, there's a subtlety with normalizability. I'm also not sure how to define the norm if you keep one of these parameters turned on finitely and try and take the overlap with it. Even on a finite volume slice, so I'm just about to say even the norm of the vacuum state is going to be ill-defined. It just has to do with fixing gauge when you try to do the path integral on the sphere. So forget about the finite volume slice. Even the vacuum itself, I'm going to say, has a problem. Okay, we could play this game, but let me say one more thing, which is maybe slightly better. First of all, because the Hilbert space is linear, when I take the derivative and I look at all these, I look at the derivatives, that actually will give me almost all directions in the Hilbert space. Now you could ask, are there some states that I get which I don't get by taking the derivative? I don't know the answer to that in some detailed way. The Hilbert space that we constructed was really taking these wave functions, taking the derivative, and looking at small fluctuations about this. You could then ask, what if you look at big fluctuations? Do you get some states which are somehow not representable as linear combinations of these states? I don't know the answer to that in detail. Okay. So,
Norm is not well defined on this compact space. That's like some UV divergence.
Let me say something about the norm in a minute. I'll come to the norm in some time. But before that, so right now, this kind of states I'm looking at are those which are finite particle number excitations on top of the Euclidean vacuum. Okay, which is you could look at infinite particle number excitations, but for now, let's just look at finite particle number excitations on top of the Euclidean vacuum. Okay. So this long digression was, there's one state which is the vacuum state. You could think of other states, but let's think of the vacuum state and think of the Fock space that you would get on top of the vacuum state. Okay? So first of all, I've been writing this sky, but in fact, I haven't been very precise with what this sky is. The way this sky is defined is you take a bulk field, some field phi, and you look at its late time behavior as tau tends to infinity. Okay. When you take its late time behavior as tau tends to infinity, you will find some terms which look like e to the minus delta tau times chi plus e to the minus delta bar tau times chi bar, where this delta is related in the usual way as to the mass of the field. Okay. If you do this, so this is what I'm calling chi. Okay. And this chi is labeled, so if this phi was labeled by a function of tau and x, then this is just labeled by a function of x. And these are projective coordinates on SD, which is my SD here. It doesn't have to be 3 to be D. Yeah. So I went a little ahead out of what my plan was, but these skies are really the late time tails of these bulk fields. Okay. So you take the bulk field, you push it off to infinity. When you push it off to the late time slice at tau goes to infinity, you will find the solution of the equation of motion has two branches. There's chi and there's chi bar. And This chi is labeled only by x, where x are some projective coordinates on ST. Okay. You always have minus delta tau, yeah, and minus delta bar tau. There is no growing solution. These are the two solutions. So yeah, so they're the two roots of this. I mean, it's not unique. There are two solutions: delta and delta bar. Delta bar is d minus delta. Okay, good. So that's this chi. What more did I want to say? Good. Okay, so you could say, well, okay, good. So now let me I have this Euclidean vacuum, and let me try and construct.
Fitting to delta and delta bar, which are, I mean, positive.
Delta and delta bar are not positive. They're complex in general. So in general, the solutions you would get to this would be d by 2. So depending on, so if the mass is very small, if it's a very light field, you will pick, then delta will be between 0 to d by 2. If orbit delta bar will be between d by 2 to d. If it's a heavy field, then delta will be of this form, and delta bar will also be d by 2 minus I nu. So this is, yeah, so this is in the principle, yeah.
These two different.
Yeah, so this is no, it doesn't matter for what I'm saying. Some of the calculations we did are in this window, but I think everything, so this other window where delta is between 0 to d, so you could also have delta between 0 to d, that's called the complementary series. And this window is called the principal series. For what I'm saying will hold for both, it doesn't matter actually. Yeah. Some of the calculations that we did, or that Ashik did actually, we did in the principal series because it's simpler to do calculations there, but you can analytically continue them to the complementary series. Yeah. Okay, good. So now you could have said, well, let me take this and let me just act with some of these late time fields and make a state. Okay, good. Now let me take these and let me act with the late time fields and let me make a state. But you will find that such a state never satisfies u psi is equal to psi. Okay? If I define this state,
it's not different. I mean, in the sense that like the x's, if you're fixing.
It is, because it's some late time thing, right? It's at arbitrarily late times. So I have some late time boundary. Yeah, I have some late time boundary and then I fixed. Yeah. So I have some late time boundary and then so it's fixed. It's some late time boundary. I don't have metric fluctuation, so I can go to this thing where the metric is flat and then I define these things. Yeah. So you could have defined something and then you could have tried to smear it out, but you will find that such a state never satisfies u psi is equal to psi. It's pretty obvious it doesn't satisfy, because in fact the unitary group, this de Sitter group, leaves this late time slice invariant and it acts exactly as a conformal group on that late time slice. So it moves the x's around as conformal transformations. You will never find a state where you take these points and you move it around arbitrary conformal transformations and the points go back to themselves. That's not possible. So such a state, you might have thought that, well, the Hilbert space is one-dimensional, there's only the vacuum. Okay? But that's not a good answer. And in fact, this question was answered by Higuchi a long time back. And what Higuchi said is the following. He said, well, you take this state and then you can do two things. You can either, let me see what Higuchi said. What Higuchi said was you take the state and you group average it. So rather than looking at this state, you take the elements of the group, you act on them in all possible ways. This is the Haar measure on the group. And you just average, you just group average this state. Okay? And if you group average the state, now you've got a new state. This state looks like it's non-normalizable, okay? Because you group average it. The group is in fact like a Lorentz group, so it's infinite dimensional. But he said, well, you should define the norm of the state as the usual norm divided by the volume of GDS. So this is this will make the norm finite. And if you define the norm this way, is the symmetry group. It's this, it's this SOD plus 1, 1. Huh? No, it's not regular. It's in infinite volume. It's infinity by infinity. Yes, you can regulate it, of course. Yeah, I'll say in a minute how you can regulate it. It's the way you fix a conformal group in string theory, actually. It's the same thing. You fix 3 points. Which I'll say in a minute. Yeah. So you take these states and you take the usual QFT norm and you divide by the volume, and this gives you a finite norm on the set of states. Okay. Let me say also, so we, by the way, also found the same answer. The way this was Higuchi. In fact, by this wave function construction, we found the same answer in a slightly different form. What we found was that the states that satisfied in the if you took the non-gravitational limits of the states we were talking about, you could write the states in the following form. Where this was a conformally, like this was a correlation function, that is f, you could think of as a CFT correlator of operators with dimensions delta bar. So you take the set of fields, you act on the Euclidean vacuum, and then you smear with a correlation function of a conformal field theory. This is not the kind of smearing you would usually do in a Fock space, because this correlation function, is not a bounded correlation function. Usually when you talk about smearing the set of field excitations, you take a field excitation, you smear it with a Gaussian. The conformal correlator is never of that kind. It's conformally covariant, so it behaves in a particular way. It goes out all the way to infinity. And this in the usual Fock space would have given you a state that's infinite, that has infinite norm. But in fact, if you divide by the volume of GDS, and I'll say in a minute how you regulate it, then you will get a state which has finite norm. Okay? So this was what we found, and in fact, we were able to show that these states were the same as Higuchi states. And how are they the same? Well, so you can think of these as group average versions of a state where 3 points are fixed. Let's say you fix 3 points, and then you go off. I'm sorry, I don't know if the board can follow, but what I wrote here is that 3 points are fixed, x1, x2, x3, and then you group average, okay? And there's a factor of volume SOD minus 1. And that is because in all dimensions, even though we are familiar with this, with this from string theory, in all dimensions, fixing 3 points fixes the conformal group up to a factor of SOD minus 1. So this is just a general statement which is true in D dimensions. So there's some factor of volume of SOD minus 1 and some determinant that you get. But up to that determinant, this you can think of as a group average version of a state that was in the Fock space, where the smearing function was a smearing function with 3 points fixed. Okay, so this here there was an integral. Sorry, I'm being a little sloppy. This was an integral over all the xi's, and here I'm doing an integral over only x4 to xn. Okay? So is this clear? What I said so far was, let me just repeat what I said. I said there's a Euclidean vacuum which you get. The Euclidean vacuum satisfies the constraints. Then you might have thought I'll construct other states by acting with the Fock space. You find none of them satisfy the constraints. Higuchi came and said, well, you can construct states by taking this state and averaging it over the whole group and defining a new norm, which was the usual norm divided by this infinite factor. We found from our wave function analysis, completely different perspective, you could write the states as the Euclidean vacuum wave function multiplied with something of this kind, where you took these operators and you smeared them with a conformal correlation function. And this state you can write as a group average version of a Fock space state where you have fixed 3 points.
So I'm not understanding. Yes. The left-hand side seems like
this
it's a unique state, right?
This is a unique state.
But the right
No, this is not a unique state. It's not unique because it depends on what versions of x1 to xn you started with. Why is it unique?
No, when you average over it.
When you average over it, if you started with a different x1 to xn, you would get a different state. It would depend on what, you see, this state depends on points x1 to xn. When you average over it, you will get some conformal. If I take a different value of x1 to xn, maybe the notation might be confusing. Here I've integrated over the x1 to xn.
Right.
So here you will get something that depends only on the cross ratios of x1 to xn. Here also you will get something that depends only on the cross ratios. So what you will get here will be the set of all. This depends on the function f.
Exactly.
This depends on the choice of points xi.
But I thought any function which is a conformal correlator will only depend on the cross ratios.
Will only depend on the cross ratios.
There are many possible functions.
There are many possible functions, and here there are many possible choices of points. You see, you can choose. So, for instance, let's do a 3-point function. Yes, let's do a 3-point function. In a 3-point function, there's a unique state. The unique state is the one where you take f to be the unique 3-point correlation function. Good, but here you might have thought there are different states, but in fact they all turn out to be proportional because you take any 3 points, you can map them to any 3. Now let's take a 4-point function. Now for 4-point functions, the set of states here is parameterized by all possible functions you have here. Right? Here you have all possible cross ratios, and that gives you the same dimension. In fact, you get a specified function, which in fact you can work out. It's some very specific, it's some delta, it's some, I have it in my notes. It's some specific function. Yeah, it's some specific. No. This state will be.
In your prescription.
No, because remember it's a linear space. So what you'll get here will be some function which sets, it's like saying you get a delta function. So it's like taking this function and setting that function of cross ratios to be delta of u minus u, whatever the function here is, with some. So yeah, let me take a function here which has x1, x2, x3, x4. Okay. That turns out to be, so let's say I wanted to get the same state by doing something here. Then I would have to make a specific choice of f.
Exactly.
Which let me use different notation. No, but it's a linear space. Yeah, but let me explain why it's the same. Let me use slightly different notation. The choice of f that you will have to make is one that sets the delta function of the cross ratios of the y there to be the specific choice of the cross ratios of the x that you chose here. So there's a cross ratio here which you get from 4 x's, right? The choice of f that you'll have to make to get this state will be you take this delta function of uy minus ux. But the set of all possible delta functions is a linear basis for all possible functions. So if I take the linear span of this set of states by putting the delta functions in different points, I'll get all possible 4-point states that way, and which is the same as making all possible choices here. Maybe the notation was confusing. Is it clear?
Yeah.
Okay.
So are the cosmological correlators are not calculated in English?
So I'm coming to that. Yeah.
The guy you also talk about 2-point, right?
There you talk about
2-point.
So 2-point functions, I'm coming to cosmological correlators. So far, I'm only talking about states. Yeah, 2-point functions, in fact, are a challenge for us. I'll say something about in the last part about 2-point functions. Yeah, you're jumping ahead, so please wait. I'll come to that. Yeah. Okay. Let me say something about the norm, the discussion that we had. So remember, I said that the way you compute the norm is you take, to compute the norm, you would take the dot product of this with itself. You would get a 2 endpoint vacuum expectation value, and you would get a square of this guy, and then you would have to compute that. Okay. What does it mean to divide by volume of GDS? It just means to fix 3 points in that conformal integral. Okay. So how do you regularize this? Dividing by this infinite volume just means you fix 3 points. We did this much more carefully in our previous paper, but it's kind of clear that dividing by volume of conformal group is corresponding to fixing 3 points. Okay, you can do it by inserting a Faddeev Popov determinant and regularizing the volume. However, let me point out that something which is that the vacuum that you started with, in fact, is not normalizable in this norm. Okay, so this vacuum does not belong to the Hilbert space. It doesn't belong to the Hilbert space for the same reason that we don't know how to do the sphere integral. The sphere integral in string theory with no insertions is ill-defined. Okay? We need at least 3 vertex operators whose positions we can fix to fix the volume of the conformal group. So the vacuum, in fact, is not part of the Hilbert space. It's not a normalizable state in the Hilbert space. It's kind of a confusing thing. It would be nice to make the vacuum part of the Hilbert space, but it's really the same problem we face in string theory when we try and do the sphere partition function. Okay? Similarly, the 1-point function also is not part of the Hilbert space. If you have a 2-particle state and higher, those are part of the Hilbert spaces, because when you square a 2-particle state here, you'll get 4 insertions, and that's enough. So the vacuum itself is not part of the norm. That's what I was saying, by the way, about the alpha vacuum and the vacuum itself. The vacuum itself is not part of the Hilbert space. Okay. So there's a problem. You might have thought it's a compact space and you could define things, but when you define the Hilbert space using this kind of a norm, which gives you an infinite dimensional rich Hilbert space, which we think is the correct way to define it, rather than getting only a 1-dimensional Hilbert space, the vacuum itself doesn't belong to the Hilbert space.
You started with the alpha vacuum instead of one series and did this.
And you'd again got 1 dimension, no?
Yes, but then
it'd be 1 state. No, but you want to be able to take superpositions of different states. So you'll have to define a norm between the vacuum and one of those alpha vacua. So you'll have the same problem. The way I know how to define a norm is you take some excitations on top of it. So if you have some vertex operator, then you can define a norm. And then, then you don't need to take alpha not 0 because it's a linear space. So you don't try and take alpha not 0 if you also have these excitations. That doesn't make any sense.
Just say that this 0 is like orthogonal to the alpha.
Then you will just get a set of orthogonal one-dimensional spaces where you can't take clean, huh?
There are excitations on top of the...
These are excitations in some directions, but I don't know how to define the norm either of 0 or of one of those alpha vacua. Now you could just by fiat say that this is 0 and this is orthogonal to some other value, and that is also, that by itself is 1. But that's some, I mean, maybe there's some way to define the Hilbert space. That would not correspond to what we would usually think of as defining a Fock space on top of this. And it would be, I think, some strange space, which would be, yeah.
Can I ask a question?
Yeah. Who's this?
Yeah, no, it's online. So just one thing. So in the cosmological context, we usually take the Bunch-Davies vacuum because for very short mode, it's because this vacuum state goes to the Minkowski vacuum for at very short distances. So it seems like a natural choice. But you're saying that there is no such state.
Well, the exact Euclidean vacuum doesn't exist. In short, well, so I'm going to say something more. Actually, I'm running very slow. I'll talk about cosmological correlators. What we usually say is that, so the exact state which has no particles on top of it doesn't exist. I want at least 3 particles to exist in the universe. That's not too much to ask. We don't care about.
I'm saying that you're saying there is no state which at short distances looks like the Minkowski.
No, that's not what I said. I just said there is no state which is completely empty. The exact Hartle-Hawking state doesn't exist. What this state looks like at short distances, we haven't talked about yet because we haven't talked about observables. I am, in fact, at the end of this talk going to give you states that look at short distances like the Hartle-Hawking state. So just to give you a preview of what I will give you states, but they are not exactly the Hartle-Hawking state. They don't look everywhere exactly like the Hartle-Hawking state. If you look at them in certain parts of space, they look like the Hartle-Hawking state with certain observables.
I see. Okay.
What I'm saying is the exact Bunch-Davies vacuum or the exact no boundary state doesn't exist.
I see.
It's not a big deal actually to say that. We are not in the exact Bunch-Davies vacuum clearly, right? Because we exist. So that we just need 3 particles. Yeah. No, it's not okay. Because of this, you take the state and you average it. So let's say you take the vacuum and you average it. The vacuum is invariant. No, you will get an extra factor volume GDS. You see, for every other state, it was not invariant to start with. So you took psi and you divided by 1 factor of volume. The vacuum is already invariant. So let's say you didn't have any of these guys. You just averaged it. You would get volume of GDS times the vacuum. You would get volume of GDS square in the numerator and only 1 in the denominator. So you would get a norm of infinity.
You can define the norm by dividing by the square of the one.
Well, but then, yes, then you'll say only the vacuum exists. So you could get a one-dimensional space by then you don't even need this norm. You could say only the vacuum exists. So if you want a one-dimensional space, that's possible. But there's no norm that can accommodate, that I know of, that can accommodate both the vacuum and these other states, because you want to be able to take linear combinations. So you can't have a special rule saying for the vacuum you do this and for something you do that, because you have to take linear combinations. It's kind of an annoying kind of problem. It would be nice to solve it, but yeah. Is it?
No, I mean, the one thing C norm is defined as just a one more integral because it's root average of 1. Like if you want psi 1 side to your product, you average over psi 1 and the psi 2 or you take any project.
No, it's the same thing as whatever. Yeah. You could, so what you're saying is you could define the inner product as psi u psi. Yes. Integral d. And then without averaging, without dividing. You could do that, but you'd again get a factor volume GDS because this u would just give you 1 everywhere, yeah? Okay, good. Okay, good. So this is actually the review part on which I spent a little too much time. So let me say something about now cosmological correlators, yeah? So in our last paper, we also defined some observables, which we call cosmological correlators, which one can think of as following. They're kind of gauge fixed observables. They came, apart from a study of states, we also had a study of observables that satisfy the constraints. In the non-gravitational limit, these guys are pretty simple. You take one of these states, and I'll write this with a double bracket. And this cosmological, correlator is just defined by taking this full, average state that you have, yeah.
So if you were not taking scalar fields, tensor fields, would there be a similar equivalence?
Yeah, there would be a similar equivalence if you had tensor fields. And these would be, so for instance, if you had the metric here, then these would be correlators of the stress tensor. Yeah.
But I'm asking.
This. I think so. Yeah, they're generalized. The same thing. You take the vector fields, and the only thing is the unitary group then also acts on the indices of the vector itself. So you take an excitation.
I was asking was that normally you have various inequivalent tensor structures. Then you have like the stress tensor correlator.
Yes.
3 dimensions.
Yes.
4 dimensions. So
2
or 3 inequivalent tensor structures.
Yeah. I think you'd have the same here. Yeah. I think so. Yeah. So there would be in the case of tensors there would be two different 3-point states or 3 different 3-point states depending. Yeah. So I think you would get. Yeah. I don't think there's a problem with that. I don't see why you worried there's immediate. You see, in the case of tensors on this side also you see.
Yeah, that side is right.
And this side I would have to write down tensor products, but write down some polarization vectors. Depending on the choice of polarization vector that I wrote for the state, I think I would get one of those 3.
Whether you would generate all of them was not.
Yeah, it's a.
Group and this is in a factorized form. You write in terms of let's say tensors.
Yeah, remember the general state here is some smeared Fock space state that you have, I don't think I don't see immediately a subtlety. Yeah.
What is the inner product between the vacuum and all of this case?
No, it doesn't exist again, right? We can't define the inner product between the vacuum. The vacuum itself, how do you normalize the vacuum?
Normalize the inner product now.
Yeah, you can take the QFT inner product. There's no problem. So let's say I define this state. Let's call this the full state. Then I can take the inner product of this with the vacuum. In fact, I'll say that in a minute. The vacuum is not part of the Hilbert space, but I can take the formal inner product of this with the vacuum. It'll give you something. It could give you some number. Yeah. No, actually later I'm going to say we'll need to project out all of these things to get states which have finite norms. You'll have to set this inner product to be 0 to get a finite norm. At the level at which I've written, you can indeed write it. I'm just about to explain that to get a finite norm, you'll have to make sure that this inner product is 0. Otherwise, you'll have a problem. Exactly. And I'll say it in a yeah.
And these x's range over the sphere.
These x's range over the sphere, projectors they range over the plane effect. Yeah. Including the point at infinity. Yeah.
But on the group action of the sphere has fixed points.
3 points.
No, I meant just in general, the conformal group, like the rotation group acting on the sphere.
Depending on
percent of the rotation group that will keep that
some points fixed. Yeah.
So you would what I'm trying to see is whether you have to mark out by the coset.
That's why you get an SOD -1. So if you fix 3 points, for instance, that is like fixing the conformal group up to an SOD -1 that keeps Then I didn't understand. Oh, you mean a model by coset? Oh, you're right. All of these states are not independent. For sure. Like you could start with one configuration of points and another configuration of points, and you might get the same state on the left-hand side. There you're kind of guaranteed to get different independent states if you start with independent functions. But you can see this very clearly for 3 points. Let's say I take 3 points. There's only one state. Now you might have thought there are so many states, but in fact they're all proportional to each other. They're linearly dependent on each other. This is what you were saying maybe. That you could, all these states are not distinct. That's a clear way to see how many distinct states there are. It's really how many conformal cross ratios there are. Okay, good. So, the way these cosmological correlators are defined is, just by taking, actually now this notation is a little bad, but these things are basically defined by taking the full group average state. So let me, I've been using slightly bad notation by using, or maybe not. No, maybe it's okay. Everywhere on the board that I see, psi is a full state. Okay, so psi, when I'm talking about psi, It's not anywhere a state which is a QFT state. So this is just defined by taking the state, the full state that you have, and just taking the inner product and not dividing by volume of GDS. Okay, but fixing these points by hand. You could ask, what is the gauge invariant representation of this operator? This is just a gauge fixed operator. The gauge invariant representation of this operator is that you could write it as psi O psi, where O is given by the integral of this set of points. So you can think of this cosmological correlator as an expectation value of the following gauge invariant operator. Or you can just think of it in the QFT space in this non-gravitational limit as just taking this inner product and not dividing by the volume of GDS. Yeah? But when you do this, you fix these points by hand. When you do this integral, you'll get the same phenomena that we were just discussing. You might find, for instance, 3-point cosmological correlators, there's really only one gauge invariant operator corresponding to all of them. Yeah? But these are convenient things to compute. It's easiest to compute in this way, rather than to look at this gauge invariant form. Okay, so the point, so the point of our current work, which I finally come to, is to try and compute in some specific cases this norm in perturbation theory and some of these observables, these cosmological correlators. So I now want to describe some Feynman rules for how we would compute them, and then describe some results, and also the question that was asked about, can you find some observables that look like the Hartle-Hawking state? Okay. Let's see, did I say everything I wanted to say? Okay, good. So there are two kinds of quantities we want to compute. One is the norm. The norm is, let me just write it here actually. So we defined some formal things in our previous paper. Now we want to do this in perturbation theory. This norm is you take the state xn f of y1 to yn vacuum chi x1 chi xn. Maybe I put a bar here, put a star here. Chi y1 to chi yn 0. This is the norm, where this is a QFT inner product. Okay, this is just the norm of the state I've written there. And we want to compute, this in this cosmological correlator. And the cosmological correlator, this is chi let z1 to chi zn, zm. And this is given by taking the same thing, f star x1 to xn, f of y1 to yn, and inner product chi bar x1 to chi bar xn, chi z1 to zm. Actually, I'm writing down and chi. The formulas I'm writing down are a little complicated, but there's too much notation. But actually, the point is pretty simple. So in the end, I said I defined some set of observables, which were like expectation values of some products of chi's in these states we talked about. We want to compute the norm. The norm is just given by taking the state, squaring it, and multiplying the smearing functions and doing an integral. This integral you have to divide by the volume of GDS, which corresponds to fixing 3 of the points. So there are 2 n points in this integral. You can fix any 3 of them. Okay? Dividing by volume of GDS means fixing any 3 of them. When I compute this observable, I don't actually have divide by the volume of GDS. I just compute an expectation value, but not all the points are integrated because some of the points are fixed by hand. Okay? So in the end, what I want to compute are just some vacuum expectation values with some points fixed. In this case, I am allowed to choose which points I fix. In this case, I am allowed to fix, my points are fixed by hand. As Ashok already anticipated, when I compute cosmological correlators, we have a trouble in defining a 2-point cosmological correlator. Okay. We have trouble defining a 2-point correlator because for this integral to be finite, you want at least 3 points here to be fixed. But if I have only a 2-point cosmological correlator, I don't know how to define that. At the end of this talk, I'll give you a different way of defining it. But in this formalism, we can't define a 2-point cosmological correlator, but we can define a 3-point and higher point correlator. And this norm is just what it is. Yeah? Okay, so in the end, what I want to compute are some smeared vacuum expectation values in de Sitter space. Okay, and they have to. Well, that would be a more complicated case. For us, we are just considering asymptotic de Sitter. No, I think there is a good way of defining a cosmological correlator of 2 points, but it's not this. It's not this set of observables. It's a more complicated set of observables. Let me go through this quickly, and then I'll come back to the issue of how one could define what we observe. I mean, we observe some 2-point correlator. Well, the question is if this is the class of observables that we should look at, or if we should look at a different set of observables which are more complicated, which are like relational observables. So at the end of this, what I want to say is, we'll compute some of these observables, we'll find some nice properties, but maybe these are not what we should think of as us observing. We are observing maybe some relational observables, which are harder to deal in perturbation theory, and it's kind of interesting if that's what we are observing. Then maybe that's something to learn, that we should be careful in defining the observables we're talking about. In those relational observables, there's no problem in defining a 2-point function. Okay, good. So, very good. So now, what are the Feynman rules? Well, to get the Feynman rules, we need one last thing. We have to now finally keep track of the wave function which I wrote earlier. Remember the wave function of this state itself, the vacuum state itself was a wave function which looked like minus G2 chi chi plus G3 chi 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 plus so on. Yeah? So the vacuum state itself can have non-Gaussianities in the wave function. Okay, good. Very good. So what are the Feynman rules that you get for this? They're very simple. As usual, from the wave function, you might get vertices. These vertices that you get from the wave function are not local vertices. This is a standard feature of perturbation theory when you do it this way. That's because these vertices are also constrained by conformal invariance. Okay? So unlike the case of ordinary quantum field theory, the vertices that you get are themselves non-local functions. That's why I've kind of drawn it, rather than meeting at a point, I've drawn it in this circle way. Okay? So these vertices are themselves non-local vertices. This you always have. This you would have even if you are just doing quantum. Yeah, I should have written the state psi. You mean I should have written psi? Yeah.
That's part of your psi, right?
G3 is part of the psi, yes. No, it's not part of, no, G3 is part of psi. No, G3 is part of 0. No. So G3, the vacuum itself can have non-Gaussianities. This is a full interacting theorem. On top of that, we are doing some other additional excitations. Yeah, maybe that's related to a next point. This is coming from the vacuum wave function. But there is also what is new about these Feynman rules is there is also a vertex corresponding to the state itself, to the bra and the ketch. So you will also get some state which comes from here, which comes from the state. So let me call this the ket. And this itself will have an f of x1 to xn, where this is the smearing function that went into the state. So the bra and the ket themselves contribute some vertices. The difference between these vertices and the vacuum vertices is the vacuum vertices can order to arbitrary order in perturbation theory. You can get 2 of them, you can get only 1 of these guys. Okay? So every Feynman diagram you draw has to have a ket vertex, has to have a bra vertex, and it can have additionally these vacuum vertices. Yeah? Okay, so are these Feynman rules clear? The main point is we are computing a vacuum expectation value and the state itself has some excitation of the fields. So the state itself contributes a non-local vertex. Then there are additional insertions that you might have which correspond to these cosmological correlators, and you also have in the vacuum some non-Gaussianities.
You have the G2 inverse?
The G2 inverse is just sitting there that you will just use to compute 2-point functions in perturbation theory.
Each of these lengths you know.
when you take a propagator. So when you have a propagator, yeah, so propagator will have a G2 inverse. Exactly. Okay, very nice. So now,
I was asking also, like, is it like an LSZ prescription? You'll not make something, you have to have the external legs.
There are some external legs here.
It's a difference between an S matrix element and a Green's function.
This is really a Green's function. It's an equal time. Yeah, it's not. It's really an equal. I mean, in De Sitter, that's what you do. You just define equal time Green's functions at late time. Maybe your question is about how you define the field. Here, one way to pick that's the difference between Green's functions and S matrices. You get something field redefinition. You can try and pick the field by conformal invariance, but that's actually a little tricky. So, you could ask about field redefinitions. Why couldn't you use a different field? I mean, right now, the way I picked it was by demanding it was a conformal primary. It had a particular conformal weight. But in perturbation theory, it turns out that itself can be a subtle question because it can get corrected. So it's not fixed, unlike.
Since if it is to be invariant, then it would have to be S matrix.
It's really like ADS-CFT correlators. You take some correlator, you push it off to infinity. So it's invariant under small diffeomorphisms, which don't. So that's fine. But maybe if you're asking about field redefinition invariance, is that what you're asking about? Why couldn't I use chi plus chi squared? You could use chi plus chi squared. That would not have the right conformal dimension. Chi is also defined right now to be a conformal primary of weight delta.
So the way you normally in a field theory you ensure that is by the LSZ prescription.
In the LSZ prescription, often we don't have this additional hook of conformal invariance. Like in ADS-CFT, you could ask the same question. You could ask what fixes the bulk field. It's the field that dies off as z to the power delta as you go to large z. So this is really like an ADS-CFT, more like an ADS-CFT correlator. You go to late times, that's like going to the boundary of ADS, and you use a particular fall-off. I'm being a little hesitant in saying that because I think there are some subtleties which in De Sitter which don't occur in ADS. In fact, the talk we had back.
Written diagrams.
You don't have to amputate them. You just push them to infinity. You put the external legs. Yeah. You'll put the external legs. There will be external legs. They'll just be there. You don't amputate anything. Yeah.
So you put
they'll just be there. Yeah. They'll be there. It's really a correlation function. It's a Green's function. Yeah. Okay. Now what, you might have first worried that when you contract all these things together, you would get a group divergence. But of course, you expect not to get a group divergence because there are 3 points which are fixed here, which are 3 points of your choice. And there are some n points which are fixed here. Yeah.
You have commutable propagators as well as multiple propagators. Your G2 inverse just looks like a multiple propagator.
Well, it's slightly different because you have a wave function here. When you compute a Witten diagram, there's an additional bulk direction that you're doing an integral with. Here, you just have a wave function. You just want to square it and compute it's a path integral. So let's say I give you a correlation function. You just take mod psi 0 squared and you integrate it. That's all.
External lines, right?
I mean, you don't have external legs except, you're really computing a Green's function. So, when you attach the external leg, you don't amputate the external leg. There's no bulk to boundary propagator because there's no bulk, but you don't amputate the external leg. There's, for instance, let's say you're computing a 2-point function, forgetting about everything I said, you would just get G2 inverse. There's no 2-point S matrix. Let's say you're computing a 3-point function. Then you would get lambda times G2 inverse, G2 inverse, G2 inverse. You would get 3 factors of G2 inverse. You wouldn't get rid of them. Right? Let's say you're computing a 3-point function. Huh? It's all in the boundary, but the question I thought Rajesh had was, from here you would get G3 times G2 inverse cubed when you computed this. If you wanted the S matrix, you'd only keep G3. You'd amputate this. Here you don't amputate it. That's all I was saying. It's a Green's function. Everything is on the boundary. There's no bulk to boundary propagator, but the propagators that you get in the boundary are there. Okay, good. So
just one notational clarification.
Yes.
So this expectation value is computed in this group average state, right? That you defined.
This is now just a QFT expectation value on the right-hand side.
I see.
The conformal correlator is already implementing the group average. Yeah.
I see. So this 0 is the usual Bunch-Davies state?
Yeah. The G2 is the usual Bunch-Davies propagator.
Okay. I see.
Okay. Good. So let me say something. The intuition here is that you might have thought that this would give you a finite answer, but of course you might have some trouble. For instance, let's say I was computing a norm of 2 3-point states, right? I could get a state of this kind, where this contracted with the interaction. So let me call this interaction lambda, just to indicate it's an interaction which is lambda. This is bra, and I could have a ket which also contracts with the interaction. This is an allowed Feynman diagram. You see, because let's say there's a 3-point interaction, I'm computing the norm of a 3-point state, I pull down 2 interactions, the ket contracts with the interaction, the bra contracts with the interaction. Now I fix 3 points. That's like saying, I want to fix 3 of these points. I don't want to do 3 of these integrals. But you still have these 3 integrals to do, and this will give you a group volume divergence. How do you get rid of this? Well, you have to make sure that the state has the property that it has no overlap with the vacuum. That's what Ashok was asking earlier. Otherwise, you would not get a finite norm. So the state has to have no overlap in the QFT sense with the vacuum. Okay? This is important, and it kind of makes a lot of physical sense because vacuum is not in a Hilbert space. So you better not have the case that the states you're defining have overlap with the vacuum. We had all this discussion about the vacuum not being normalizable. And so in perturbation theory, you have to make sure that, in free field theory, it's very easy to make sure the states have no overlap with the vacuum. You just normal order them. But in perturbation theory, it's harder, and you have to make sure the state is corrected so that you have no overlap with the vacuum.
So it's automatic in the norm?
No, it's not automatic. You have to take linear combinations of states so that they have no overlap with the vacuum. So the norm doesn't automatically ensure this. Okay. Similarly, for the cosmological correlator, let me just go through it fast. I won't give details. The cosmological correlator also turns out that these correlators by themselves might not be well defined. The correlator you need to define is some smeared version of those correlators, x1 to xn. This is a compact smearing function. It's not a conformal smearing function, which has the property that this function, if I go to momentum space and I set one of the momenta to 0, goes to 0. And if I set the sum of 2 momenta to 0, then also it goes to 0. That's important also for removing other kinds of divergences that might occur. And also that you have to take the right linear combination of n-point correlators so that the vacuum expectation value of this is 0. Once again, in free field theory, it's just normal ordering, but you have to be careful. And these are things which eminently make sense. This is actually the statement that the cosmological correlator doesn't have any 1-point contribution. This is the statement the cosmological correlator doesn't have any 2-point contribution, because remember I said we have trouble in defining a 2-point contribution. And this is the statement, it doesn't have any overlap with the vacuum. So these are all conditions you need to impose to make things finite, and they make a lot of sense. In perturbation theory, we find these conditions. If you didn't impose them, you would get infinities. So it makes sense you have to impose them. Okay, good. Now let me say one thing about results, and then I'll spend 10 minutes talking about relational observables. So, Ashik has computed actually many of these diagrams, and we find many interesting results. The nice thing about doing these kinds of integrals is that, they're basically conformal integrals. So there are all these results on harmonic analysis for on the conformal group, where people compute these integrals, and we can find, so if we choose our states appropriately, we can find, interesting results for cosmological correlators. For instance, let's say, we can choose the case where the vacuum itself is Gaussian. So let me choose the example. So an example is take the vacuum to be Gaussian. Then, in the usual story, there would be no non-Gaussianities. But in what we are saying, you could get a very specific form of non-Gaussianities which would come from these external excitations on the states. For instance, if you take the state which is a 3-particle state, let me write it as 3 plus 4. Then you can compute in this state a particular kind of cosmological correlator, and you will find a conformally invariant answer with a particular number with a number that we can compute. But you will get a specific non-Gaussianity in this case. You won't get higher non-Gaussianities because the number of external vertices that you have is limited, but you will get a specific leading non-Gaussianity. Similar, so the punchline is that we can get interesting non-Gaussianities, even when the vacuum is Gaussian. Even okay. Well, why is this happening? It's kind of not a mystery why it's happening. It's because the background has some particles sitting in it. Usually what would have happened is the background, if you just thought about the same problem in quantum field theory, you could have said, I'll just put some particles in the background. But you would not have got a conformally invariant answer. Here, the fact is that the answers you get are always conformally invariant. They're always de Sitter invariant. That's guaranteed. In fact, we can prove that the answers you get are always de Sitter invariant. So you get some interesting new class of de Sitter invariant answers. Some interesting, there are no interesting shapes in the case of 3-point functions because the shape is completely fixed by conformal invariance. But for 4-point functions, you could get interesting classes of shapes that you might not have got from a Hartle-Hawking vacuum. For example, if you look at the Hartle-Hawking state, the kinds of functions that you can get are constrained by the fact that the Hartle-Hawking state comes from doing a no-boundary path integral. And when you do a no-boundary path integral, there's a specific set of wave functions that you get because the interactions that you have are local. So for instance, these no-boundary path integrals give rise to cosmological correlators that are well known to have a specific pole when you set the sum of mod of ki to 0, okay, which we explored a long time back in the ADS-CFT context. But the cosmological correlators also have this. In this case, you could get at 4-point level some states which don't 4-point functions or which don't necessarily have those poles. Okay, so because you're not constrained here to take states which come necessarily from locality as you are in the Hartle-Hawking case. Okay, so you can get interesting non-Gaussian features. Someone might say that that's wrong. You shouldn't get those non-Gaussian features, but we have a way of generating such interesting non-Gaussian features. And these can occur even when the Hartle-Hawking state itself is Gaussian. And beyond that, if you look at higher point correlators, they are not necessarily constrained as people constrain correlators in the cosmological bootstrap. For instance, they could have these unphysical poles, as I said. Okay, yes. Yes.
Suppose create some 2-part.
Yes.
So why do they affect the correlation function?
They affect the correlation function because that correlation function is secretly non-local. This correlation function as I'm defining it, and maybe that's what I'm now about to say. It's the simplest kind of observable you can define in the gravitational theory. But remember, there's no local observable in the gravitational theory. So this correlation function is a gauge fixed correlation function that looks like it's labeled by these points Z1 to Zn. But actually, its gauge invariant description is a non-local description which is integrated on the whole slice. And that's why when you created these 3 particles, it actually probes the whole slice and it knows what is happening. Also, you have to create 3 particles in a specific way. You have to create them, you have to spread them out on the slice because it has to be de Sitter invariant. And then the correlator itself kind of probes the slice and determines what's happening. So even though, yes. Yeah, that's the intuition. Yeah. I'm about to say how you would realize the intuition, but in gravity, if you look at simple states like light states on top of the Hartle-Hawking vacuum and simple observables, that intuition is not correct because the states that you have to are themselves diluted in a particular way because they have to be de Sitter invariant. The observables that you have are also diluted in a particular way. So low point observables can always detect which state you're in. They don't get diluted even at arbitrarily late times. The low point finite observable. Huh? No, this state is what Ashok is saying is the usual intuition we have from inflation is you put some excitation, you went to late times, it got diluted. If you measured 3 points, it looks like the energy density is infinitely diluted, and therefore how would you see it? But if you look at simple observables in gravity and simple perturbative observables in gravity and simple perturbative states, that intuition is not realized. I'll spend the last 10 minutes explaining a different set of observables which are actually more complicated that will realize the usual mundane notion. Yeah. 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 If you just define Fock space states, which are not de Sitter invariant. Yeah. Yeah. It's also a question of what observables we are looking at. The observables we are looking at are also secretly diluted because they are, so, when you scale them up so that you get finite values, they kind of run over the whole slice and they determine what's happening. Even though they look like they're localized, they're not actually localized. Okay. So the other point is none of these states look like the Hartle-Hawking states. So they will already look like HH, look like, because all of them, have some excitation on top of the vacuum. So you can always distinguish them from the vacuum. So now you might have thought, what about this intuition that, if you wait long enough, everything should look like the Bunch-Davies vacuum. Okay. So what happened to that intuition, which is what you asked about and which is what the question was about also. So I now want to describe a different set of observables that will realize this local intuition of ours. This issue actually, by the way, is the same issue that we have discussed also in other contexts, in the context of ADS and flat space, which is how do you get mundane locality in a theory of gravity? Okay. So let me say 2 minutes of philosophical spiel and then I'll give you a construction. You see, in gravity, we have a problem, which is there are no local gauge invariant operators in gravity. Okay. So we have a problem with that because, it looks like all the operators we have to write down are non-local. This also leads to interesting results. For instance, in this case of cosmological correlators, we showed that if you took cosmological correlators that were an arbitrarily small open set, just labeled by points an arbitrarily small open set, you could completely identify the state. So the version of what we call holography of information here is the statement that if you take correlators in a very small region, by that I mean you take these points in a small region, of course the gauge invariant description is spread out, that's a complete set of observables. Okay. Similarly, this leads to these results on holography of information that we had with Alok and others, which is the statement that, in the end, if you measure observables at infinity, you can completely detect what's happening inside because there is no way to strictly localize operators in one place. Okay? So this is, so now you would say, well, but, physically it looks like I'm allowed to localize operators. I'm making a measurement here and not somewhere else. So how does that work, right? So this fact eventually, I think this thing that I just said, really it's the manifestation of holography that you can make no state looks like the Hartle-Hawking state if you take those correlators in any region. Okay? So one way to say that kind of dramatically is you look at cosmological correlators, arbitrarily small region of the open slice, they have information about the full state. Okay? So holography in De Sitter, one might say, works this way. It's like a point in De Sitter has information about the whole slice. Okay, other people come to the same conclusion in different ways by saying you look at the entanglement wedge of a point and you get the whole slice. However, you clearly want some notion of approximate locality if you want to talk about cosmology. Right? You don't want to say that we can measure everything here and determine the whole universe. So I now want to give some philosophical feel about how you can get usual notions of locality. And I want to make an analogy between holography in gravity and unitarity in QFTs. Okay. So in both cases, they're true as exact statements. Okay. So if you ask for, let me ask it here. Okay. If you ask for an exact statement, if I give you all correlators exactly in an arbitrarily small region, then I can determine the whole state. Similarly, unitarity is true as an exact statement. Unitarity in quantum field theory is just exactly true. Second, you can ask questions about perturbative observables in simple states. So you could ask perturbative observables in simple states. And then you can see signatures of holography in gravity, and you can see signatures of unitarity in quantum field theory. When you compute the S matrix, you do perturbative calculations, you can see unitary, right? That's what we ask our students to all check. So, and that's what we are seeing here. We are seeing the fact that you make a probe in one region, you're kind of sensitive to what's happening elsewhere. But there's a case in which unitarity fails, and that is you take a heavy background and you coarse grain observables. This is the discussion, this was the discussion we were having in the talk yesterday, which is fundamentally the world looks unitarity, but you see dissipation and irreversibility all around you. If you take a heavy background and you coarse grain observables, then of course you don't have unitarity, right? It's the fact that nobody can tell me what was the velocity with which I threw up the chalk, because all of you coarse grain the velocity of the chalk and you didn't keep track of lots of fine grained observables that had track of this. And that's also true of holography in gravity. If you take a heavy background and you coarse grain observables, then you lose features of holography. So if you coarse grain, you will get information loss. If you fine grain, you won't. So, I said that none of these states look like the Hartle-Hawking state, but I now want to describe this last regime and how this would work. And I want to say if you take a heavy state, which is not in the perturbative discussion that I've had so far, and you coarse grain observables, which I'll describe in a specific way, you will again recover the usual local description of Hartle-Hawking state. So I'm a little over time, but I'll try and do this in 5 minutes. Yeah. Okay, is this philosophical story at least clear, the philosophical slogan? What I want to say? Okay, fine. This is the point where you should. What is the limit on? Very high, probably suppressed by, I think, it's like asking on locality in the LHC, right? Probably very high, probably e to the minus s, where s is the entropy of the detectors that you have. Entropy of the detectors. The fine-grained entropy of the detectors, number of states you have. Very high, probably. It might be, well, maybe there's some interesting thing you can do to make it lower, but certainly a quantum gravity. Huh? So so the simple constructions you do, the simple kind of thing you would say is it's precise to all orders in perturbation theory, and it breaks down, at e to the minus s, where so that's the simple kind of thing you would do. But you could try and make it more precise in a more specific example if you had. It's really the question of at what level would you start seeing unitarity in the everyday world? You can make that precise also. So we could make it more precise. I'll give a construction here and we can ask the question more precisely in that setup. I'm now just about to describe this regime. In what sense should we expect the universe around us to look like a Hartle-Hawking state? So let me go to QFT and let me take a heavy background QFT state. What is the kind of state I want? I want a state that on the late time slice has an excitation. Let me call this state psi b, which is kind of living on one part of the late time slice. What I'm saying right now is just quantum field theory. This is a quantum field theory state. It's not one of my group average states. I want the state to have some property. I want it to have the property is basically much smaller than 1. Yes. Let's ask the question here. Yeah.
Do you make it as accurate as you want by making the detectors big enough?
I don't know about LHC. Can you ask me this question in 5 minutes? Because LHC we'll make it more precise. You can please ask me the question here. Yeah. Just 2 minutes, please, since I'm already, I think people are already a little tired. Okay. So I want to say, I want a state which has the property that if I act with one of my de Sitter elements on the state, I get a state that's almost orthogonal. How do I generate a state like this? If you have a state with a lot of particles, it's a heavy state. If you act on it with one of the de Sitter isometries, you move the particles around. If you move the particles around, you will get a state that's orthogonal to the original state. Because if you take the chalk here and you move the chalk a little bit, remember the chalk is a classical state. So the chalk here is completely orthogonal to the chalk somewhere else. That's not true if you just have one particle wave function spread out. But it is true if you have a localized classical state. So I want this property. Second, I want this to have the property that if A is some quantum field theory observable that's localized in a different part of the late time slice, then this gives you the vacuum expectation value of A to good accuracy. The accuracy of my construction is going to depend on the accuracy of these two statements, so we can make it precise here. Okay. So you agree that in quantum field theory, it's easy to find such states. I take a classical heavy background that's localized in one part of the late time slice. And because it's localized in one part, observations made in another part in quantum field theory look like the vacuum, and it has this property. Then I'm now going to define group averaged observables in a group average state that have the property that they look like vacuum correlators. And the construction is as follows. Let me define the group invariant state. Let me call it psi observer, which is U psi background du. That was the QFT state, but this is the quantum gravity state. It's an average version of that. So it's the case where I take this and I average this with a conformal group everywhere. Let me define the operator A hat to be where this is not quite a projector, but rather it's 1 over n times psi background. It's some operator. And n is this quantity. Okay, so it's some normalization factor. I can explain to those of you who are interested. But this projector has the property that if I now take this, so let me first point out, this is a group averaged operator. I've averaged over the whole group. So this operator is a delocalized operator. This is a delocalized state. But I claim if you take expectation values of this operator in this state, you will get vacuum expectation values. And let me just show that and then I'll stop. And this is my coarse-grained observables in heavy states. So let's look at psi observer, A hat psi observer. So what you'll get is 1 by volume of GDS. Then you'll get these projectors. You have a group average here and a group average on the left also, from the bra and from the ket. Yeah? But notice that this projector, as I've defined it, it's not a projector actually, it's a rescale projector, has the property that this looks like delta function of U and identity. And the reason it has that property is because of what I said here. If I look at psi background, you see this projector is almost psi B, psi B. So if I look at psi B, U psi B, it's basically 0 unless U is the identity. Okay? Otherwise, it could be something non-zero, but the normalization factor is such that if I do an integral over the whole group, I'll get 1. That's how the normalization factor is defined. You can kind of see that it's the case. Yeah? Huh? Yeah, of course. Okay, good. So now let's take this expression and let's insert it here, and you will see that you will get dv1, dv2, dv3. These are all dummy conformal integrals. You will get psi b v1. That's from the ket. Then you will get this v2 pa v pap. V2 dagger, and then you'll get V3 psi B. I just call the U's V's just to differentiate them and point out there are 3 V's. This is the ket, group average. This is the ket, this is the bra, and this is the operator in the middle. This projector sets V2 equal to V3. This projector sets V1 equal to V2 dagger. Okay?
Oh, that is actually V1 dagger.
Huh? Oh, this is V1 dagger. You're right. Thank you. So this sets V1 equal to V2. This sets V2 equal to V3, right? So these two projectors set V1 equal to V2, V2 equal to V3. You get rid of 2 integrals here. You're left with only 1 integral, but that integral is not occurring here anywhere. So you just get integral of D, that cancels with this volume of GDS. So you just get the expectation value in the background state of this QFT operator. But remember that I said to be this operator. So this is just this. So this is an example of what one might call a precise construction of a relational observable. What I've done is I've taken this heavy background state and I have defined some operators that are dressed with respect to the heavy background state. These are all words. This is the precise notion of how you dress the operator. But physically what you're saying is there's some background. I'm dressing the operators with respect to that background. I have to make the configuration de Sitter invariant, but I take the whole configuration and I average it in a de Sitter invariant way. Okay? So by doing that, it's true that the state itself is average, the observable itself is average, but the particle is always fixed with respect to the background state. Okay? So this is an example of an observable, of a coarse-grained observable that will give you vacuum expectation values. The answer to Ashok's question here can be made precise of how precise can you make it. It's the fact that this is not exactly a delta function. So you would have to put a lot of heavy particles here to make this look like a delta function, and you could ask how sharply can you localize? How heavy a state can you have so that if you make a conformal transformation, you get something that's orthogonal for a very small conformal transformation, and then you would have to make sure that this quantum field theory state satisfies this property. In the end, there would be some small corrections. So if you asked an exact question, you would see that this was not exactly the same as the vacuum expectation value, but this is a place where you could make this precise. Yeah. Okay, so let me stop here. Thank you for your attention. Just to summarize what I said, I said there's this, we analyze this class of states in quantum gravity which satisfy the constraints. You can write down a simple set of states and simple observables. You can make calculations with them in perturbation theory. you find interesting answers. You find a new source of conformally invariant non-Gaussianities, even when the background state is a Gaussian. This is kind of nice, or you might think it's kind of nice because it gives you a new way to generate non-Gaussianities. But then you might also object that maybe these are not the observables one is measuring, and maybe that is so. So one could ask, what are the observables one should measure to recover our usual notions of locality? And then perhaps the right answer is you should measure these kinds of relational observables, so that even though the vacuum state is not part of the Hilbert space, you can get some observables which look like they are vacuum observables. Even though all observables really are not local, you can get some relational observables that look like they are approximately local. However, I think this is kind of an interesting thing if this is what is happening, because I think these operators that we've defined, note they're state-dependent operators, because they only work if you insert them in a particular state. They would not work if you use those same observables in a different state. So it's an example of, again, state dependence solving some problems that quantum gravity creates for you, but then you might want to ask questions about, the consistency of state dependence. Why is it that we as observers choose to observe these operators as opposed to some other operators? So I think there's some interesting question there. Also, there's all this work on, exact properties, quantum field theory in de Sitter space and so on. And if it is really true that you're not measuring simple perturbative observables in simple vacuum states, but you're really measuring these more complicated observables in a heavy background, then maybe one could also revisit some questions people have about, unitarity or infrared instability and so on. So if these are really the observables we should consider in gravity, then that's an interesting thing. Okay, so I'll stop here. Sorry for going over time. Thank you for your attention. Yes, here you can define a two-point function. This is because it's a vacuum correlator. So I can put a two-point correlator here. This A is any observable which is localized here. I can put a two-point function here, and I'll get exactly the vacuum two-point function. This was in the QFT, but this operator A hat is now in the gravity theory.
The last line when you went
here
that
is a QFT answer.
But that's it's like, but the zero is defined then not as the Hartle-Hawking vacuum.
No, it's a Hartle-Hawking zero.
But,
so this is a QFT expectation value.
I mean, I thought they are different.
Okay, yes. So this is a so this is a QFT state. This is QFT.
Yeah.
Then I defined this state, which was a quantum gravity state.
Yeah.
By averaging the state over the group. So this is a new state. This is a different operator which is taken by averaging the QFT operator over the group and putting these projectors. This is not a low point operator. Now I look at the expectation value of this operator, the quantum gravity in this state. It turns out that this expectation value you can show is the same as the QFT expectation value of the QFT operator in the QFT vacuum.
Last step in this, which
that was confusing?
Yeah.
Yeah.
Because you went clearly, you did all that, you said that we want delta function.
Yes.
All that comes, then you get something psi B, A, B, psi.
Yes, but remember in the QFT, this expectation value. No, P acts on psi P is 1. You see P, V2, V3, I use the delta function. This P is also gone. In the QFT. No. You see the gravitational norm and the QFT norm are related by this volume GDS and these integrals. The gravitational norm is the QFT norm, but with this divided by this volume of GDS. The volume of GDS cancelled because there was one unitary group that didn't get soaked up by a delta function.
So in that,
there are three. Here.
Observable is in the
this is the so when I write these brackets, I mean the quantum gravity norm. Yeah. The quantum gravity norm is the QFT norm divided by volume GDS by an infinite volume. So the quantum gravity.
The states are there. There is no.
Here, no. The state is just defined with the group average. This is the quantum gravity state. I don't define the state with the volume GDS. This is the quantum field theory state. I average it over the unitary group. I get a quantum gravity state. This is a non-normalizable state in the quantum field theory. The quantum gravity norm is the quantum field theory norm divided by this infinite factor. So all these states are non-normalizable in quantum field theory, but formally I can define the QFT norm and divide by this infinite factor. Now here there were three integrals over the unitary group. Yeah. Two of them got soaked over and one of them got cancelled. So it turned out that the quantum gravity expectation value turned out to be the same as the quantum field theory expectation value. I mean, it's not surprising because we constructed the operators by design to have the property that the quantum gravity expectation value turns out to be the same as the quantum field theory expectation value. Yeah.
can satisfy that first phase later.
This one.
Suppose you construct a psi field which satisfies that first.
That's actually quite easy, yeah.
But then there's possibility.
Yeah. None of them are exact. You see, both of them can't be exact. Both are, oh yeah, sorry. This is also an approx. Thank you. This is also an approx. Yeah. So this is the question Ashok is asking, how good can you make the approx? You can make it pretty good, but you see, these things, it's hard to analyze how hard, so how would you, you have a question, Ashok? You can ask, then I can answer, yeah. Please.
So I want to ask
Yes. Yes.
Suppose I want the tax space. So that you understand. So, and yeah, suppose you have a theory which has some exactness. I want to focus on some particular S matrix element. I have to measure it to up to some error, right? I fix my error.
Okay.
This is my error. And in that case, you have to make a detector big enough.
Yes.
Have a space big enough, and you measure.
Yes.
You can make that measurable within that.
Yes, yes. Can we work in ADS? That's even simpler.
Okay. Now
let's work in ADS. But can we work in ADS? Because flat space, are you worried about the infrared issues, or we'll work in ADS? Then entropy is finite. Okay, fine. Okay. Yeah. The entropy is just infinite because of volume of space. But please go on. Yeah. Yeah.
I have the same question in that.
Yes.
That I have to, there is an S matrix element, I have to measure it.
Yes.
I allow the same error bar. Right? And I have to know if I can make a detector big enough. I have a finite amount of space. Right?
Yes, yes.
I cannot make it arbitrary large, but I can make it large.
Yes.
So is it possible to measure the same S matrix with the same accuracy with a finite but large enough detector with a finite but large enough space? Large enough region of space.
Yeah. Is it possible to measure the same S matrix? So there would be the usual quantum gravity corrections anyway. What you want to ask is, can I?
Exact S matrix in quantum gravity.
There's an exact S matrix in quantum gravity that you could measure.
Measure by using a finite detector in a localized instrument. Provided you allow some small error, right? You fix that error as you make it as little as you want. Once I decide on the error, then the engineers tell me how big a detector I need and how much space I need. Right?
Yes.
Is that going to be possible, or you think it will not be possible?
Can you make the error arbitrarily low? You mean that's your point? Yeah, before something collapses into a black hole or something. That's the kind of concern you would have, right? If you try to make the detector too high in your finite volume, too heavy, then something might collapse into a black hole. So you might. So there might be a finite accuracy. There might be an ultimate bound to accuracy if you have a detector. So let's say you fix the volume also. Then you are allowed. So depending on your accuracy, you can take the volume to be as large as you like. Okay. I don't know. I would have to think about the question, but yeah. There is a scale that comes from the energy of the S matrix, of course. Your S matrix itself is measuring particles of some energy. So that will itself generate for your scale, which will be just energy into divided by m Planck. So if your particles themselves have energy by m Planck, if you're measuring particles of energy E by m Planck, that will give you already some notion of entropy. So now you can ask, what? So there are already quantum gravity effects that are suppressed by this parameter, that is E by m Planck, that are going to change the answer. And now you could ask what you want to say about R.
If you cannot measure it using finite volume, right? Then that quantity doesn't exist, right? Because ultimately the S matrix is the infinite volume limit of some finite volume experiment, right?
But sorry, but why are we talking about the S? Why are you worried about the S matrix? Here I wanted to talk about local observables. Maybe that's what you want to talk about.
I want to know,
the S matrix, there's no problem anyway. Yes, but I think the S matrix, there might be no problem in defining, right? In quantum, because that's a well-defined observable at infinity. Yes. I would not think there would be a problem also in working in finite volume if you allow me to take the volume to infinity.
No, not to infinity.
Correct. And so if I take the volume to be large enough, then I think, in fact, Ashik and so on were doing these things where you try to look at finite volume and finite volume effects. But I'm not sure, I'm not understanding why that's relevant to this issue.
No, I'm not asking what is the intrinsic difference between flat space and the absence of gravity and
the intrinsic question has to do with define. Yeah.
I mean, the Gaussian law here told us that you had to question by the visitor group.
You had to?
Yeah.
Flat space.
No, flat space we don't do that. Like we don't anticipate, but
flat space answering one of the essential difference.
Because when we zero limit,
No, but the essential difference between gravity, it always has to do with the question of, from an experimental's viewpoint, the essential difference has to do with local observables, never with defining an S matrix. So the essential difference has to do with the fact that there's something you can measure at infinity. So let's say I'm at finite volume. You could ask me the following question. How well can I hide what is happening in the bulk of this room from what's happening on the walls of the room? Before, so let's say I'm in the bulk of the room, I give my detectors around only a epsilon time. So they can't wait for light signals to emerge. So I'm going to now switch on a light or not switch on a light. And the people around can't wait for light signals to emerge. And you can ask, how well can I hide what's happening from them? Before, if they only have time to measure, which is smaller than the light crossing time of the room. That is the kind of question for which you would find an essential difference. The S matrix is an observable where you send something in the far past, you measure it in the far future. So if you ask a question which is a slightly different question, which is you make an observation at an instant. Yes.
Find that.
Yes.
But I can make that measurement as accurate as I want by what in a local way. So even in quantum field theory, the correlation functions are either. They change under field.
But this is a slightly different question, right? Because the question that I want that would be different in gravity, again, maybe I'm missing how it's directly relevant to this one, is the question of, actually this is the kind of question that Ashik and Nava were asking, which is, so let's say I have a chalk here. Can I measure, so I can measure the fact that it's a chalk and it's not the vacuum by making a measurement in gravity and the boundary of the room. And I can tell you how accurately I have to make that measurement. I have to be able to measure, the Gauss law accurately enough to determine that the chalk exists. That's the difference between gravity and not having gravity. So you might have thought that you're making a measurement which is a local measurement. So it should be insensitive to whether the chalk exists or not. But it's not insensitive. It is sensitive to whether the chalk exists or not. Then I could ask a more refined question, which is I have a red chalk or an orange chalk. And can I determine? In quantum field theory, the answer is no. You can never determine till light goes to the boundary. But in gravity, I can determine instantly, by making the right measurement.
Quantum field theory also all that invariant.
So there is no issue of the SMA in gravity. Our result was actually that you look at all correlators here, which are the full S matrix, and you can in fact get the same correlators by measuring gravitational observables in the past boundary, and that would give you the same information as the full S matrix. So there's no dispute that all the information is in the S matrix, but there's something I can do here which I cannot do in quantum field theory, which gives me the same information as the S matrix. So in quantum field theory also, you could have waited for long enough and you would have determined if it was the orange chalk or the green chalk. But in gravity, I would do it in a, by making measurement. Yes, I think so. Sorry, anything means this. There are some things you can do in gravity which you can't do in quantum field theory.
So that's
yes.
Other.
Okay, okay, yes.
So what is then is one correlation function that would define.
Yes.
Why can't you define it as accurately as one? In gravity, because in quantum field you can define that.
Well, this is this issue that Alok was mentioning. This is an issue which is specific to de Sitter space. In the case of flat space, we don't have this issue at all, which is that the 2-point function is just well defined in gravity and so in flat space and in ADS, this issue is not there. There's a 2-point function which is defined in field theory. There's a 2-point function which is defined in gravity. It's this annoying fact about gravity in de Sitter space. I don't know a deep philosophical reason why you can't define the 2-point function or why you can't define the vacuum reason. Is this annoying fact that to fix the conformal group we need 3 points. We can't define a 2-point scattering amplitude in string theory as well. One could ask that also. Why can't we define a 2-point function in string theory? I don't think this issue of that specifically the 2-point function not existing is a philosophical issue about gravity. It might be even maybe there's a technical way that might actually just let you define it, just like maybe there's a technical way to define the sphere partition function. So I don't think this 2-point function defining or not defining is the key issue. I think the more interesting physical issue is the fact that there is higher point functions, 3 and higher point functions that you can measure in one part of space that look like they're sensitive to the whole state in gravity. The fact that we can't define a 2-point function at all, I don't know of a good reason for that, which is a more fundamental physical reason. Well, that was your question? Yeah. The other question you asked about the accuracy you would have to fix here. You could ask this. That's the question I was asking here. How well can you hide what is happening in the center of the room from the walls of the room? That's a question of how well you can construct states that have that. And in the end, at some point, you might find that you can't localize a state arbitrarily well. It always spreads out or something else happens. So there might be some fundamental bounds to that. But it's a precise question. I don't immediately know the answer to what the bound is. But you could try and ask the question, and I think it's precise here. How well, those approximate signs, what is the real error there? Okay, yeah.
Definitely what
Ah,
was
ah.
earlier about like, you could try to define the two-point function just because there is a time translation really speaking in the actual inflationary scenarios that we.
Oh, so if you work in inflation, then indeed it might be different. So I have not thought. Actually, we should have thought carefully about it. If you're not an exact de Sitter, but yeah. So you might use, for instance, the inflaton itself as a clock. If you use the inflaton as a clock, then you might be able to do more. But yeah. So that's a little like this observable. It's this observable that I defined is little like it's using a background, right? So in de Sitter, everything was featureless. You introduced a background, so if you had a clock, you might be able to use that to define other things as well. It's a lot like these last observables. Yeah, so you would think of the scalar field as the background state.
But then you would say that when we say we are measuring A, you are actually secretly measuring A.
A hat, yeah. So that's actually an interest. Yeah, exactly. So but you see, this is the kind of thing you probably are doing. Like you are maybe using the galaxy and so on to set some reference frame and so on. On the other hand, it's this looks like a nice thing, but these properties really it's a different operator from A. So when you think you're measuring a simple operator, you're actually measuring a complicated operator, which happens to look simple. I think that's an interesting thing. I mean, it's worth thinking about more if that's really what's happening.
Okay, so no questions.
Yeah. Okay, thank you.